Hello everyone, and welcome to the CalcPlot3D introductory video. Today I'm just going to introduce you to the basics of using this applet. So first off, you can access this applet through the following web address up here. It is free, there's nothing to download, and fortunately it also can be accessed on a mobile device. So once you're at the site, this is the example that you'll always see when you first load CalcPlot3D. So let's look at a few ways to interact with this graph. First off, we can rotate this object around by clicking on it with the mouse and rotating it in various directions. In addition to this, there are several keyboard shortcuts for rotating the figure around. So for example, the left and right arrow keys on the keyboard will rotate it about the z-axis, and then you can also use the up and down arrows to rotate it on up and down on the screen. Okay, so let's say you get into some really strange orientation and you want to just reset it to the default view. You can click Home or Function left arrow, and that'll bring you back to this orientation of the figure. There are actually a lot of keyboard shortcuts in CalcPlot3D that you can take advantage of. For example, let's say I want to rotate about the x-axis. So to do this, I would click X and left or right arrow. I can see that the figure rotates about the x-axis. Likewise, we can do the same with Y, and the left or right arrow accomplishes a rotation about the y-axis. So if you'd like to know a bit more about the keyboard shortcuts available for CalcPlot3D, you can access them through the following means. We go up here to the menu, and there's a help manual, which comes in really handy. So in the help manual, we can see rotating and keyboard shortcuts. There's a whole list of really handy keyboard shortcuts for CalcPlot3D. So that's how to access the help menu to learn more about those. Taking a look up here in this region, we see a bunch of handy buttons. For example, magnifying glass with the plus sign is going to zoom us into the figure, whereas a magnifying glass with the minus sign is going to zoom us out. So those are some really handy buttons, especially for students. If part of their graph is appearing but they can't see the whole thing, they can easily use these buttons to zoom in or out as necessary. And then right next to that, we see the 3D glasses symbol. So this puts the figure into a form that would be compatible with any standard pair of 3D glasses. It's actually something really fun to include in the classroom. Additionally, we have magnifying glass that turns the surface into transparent, and hitting it again will get rid of that feature, make it opaque again. This E removes the edges, so all of those trace lines can be removed if you wish, and F would alternatively remove the faces and give you a wireframe. So those are some of the readily handy buttons available to interact with. Finally, if you'd like to zoom in on the figure, for most trackpads that would be a 2-finger zoom, would bring you closer and further away, as well as a right click, you can actually drag this to different areas on the screen to get a better view. So let's go ahead and take a look at what other features are available for interacting with the graph. Here we have an axis formatting option where we can change the window in which we view the figure. So here, if we'd like to, for example, view this figure constrained to the first octant, we could set the x, y, and z values to be 0, and then we only see the first octant. So this is an example where this right click and drag would come in handy to get the object back into the view of our frame. So you can control the minimum and maximum x, y, and z values for the window of view. You can also control the tick marks. So maybe, for example, let's go a little further in x, let's go out to 5, and maybe we want the x ticks to be every 2 increments instead of every 1. Okay, and additionally, these menu options are the Z clip. So let's say, for example, you don't want to see anything in the graph above z equals 1. You could clip the figure at that value of z. So that's what the Z clip does. So that is the Format Axes panel. Moving now to this Grid Lines menu, we can see various options for things that we wish to show in our graph. So for example, maybe we want to show some grid lines. We can show them down there at the bottom of the box or actually on the XY plane. Additionally, we could turn off the box, and if these axis markers weren't important and we wanted to get them out of our view, we could remove them as well. And finally, you also have the option of removing the axes. Okay, so a lot of different view options there depending on what you're trying to illustrate in your graph. Lastly, we have the 2D trace plane. So here you can look at different XY inputs for the function. So you can click anywhere in this grid to add a point on the graph of the function. So as an alternative to clicking or moving this around anywhere you'd like with your mouse, you could also input an exact value. So maybe I want to be at 1, 1. You can input that exactly. And finally, you can also use the sliders here to change the value of X or Y. Okay, so once this point is on the graph, a bunch of different point-wise properties become available to us. So clicking this gray arrow down here, we see a bunch of different point-wise properties that you might want to look at for a function. So for example, tangent plane at a point. We now have a point defined, so we can add a tangent plane to the surface at that point. Additionally, we could drag our point wherever we'd like and watch the orientation of the tangent plane move. I think this is a really great illustration for students during class. Some other pointwise properties that are helpful to show. We have the gradient vector. We know the gradient points in the direction of greatest increase of the function. It's a two-dimensional vector here. At this particular point of interest, the gradient vector is shown in red. Another pointwise property that is quite nice are these fx and fy traces for the tangent lines. So in order to discuss partial derivatives, I will often add in an fx or fy trace line. We can see the slope of this black line representing the partial derivative with respect to x. Several other pointwise properties here that you can explore, for example, directional derivative. So I'll leave it to you to explore those a bit further, but I wanted to draw your attention to the fact that once you introduce a point input, you have a bunch of excellent pointwise properties that you can include in the graph. So as I mentioned, every time you open CalcPlot3D, this particular example will appear. It's the function shown here, and it's graphed in this particular example from the x and y values from -2 to 2. You can certainly change this as well. So perhaps, again, let's say we want to constrain x and y to be positive values. So this is a bit different than changing the window, right? We're just changing the inputs of the function, and so the graph has changed accordingly. Right, so earlier we explored this button where we can zoom in and out. So if I zoom out on this particular graph 2 times, I can see that it's becoming quite faceted, right? It's becoming quite peaked and maybe isn't representing the function very accurately. So we can control this using the number of grid lines. So for example, maybe I'll increase this to 60. And if we take a look at how the graph changes, we can see that it's smoothed out quite a bit. Okay, so a number of grid lines controls the discretization of the surface. So we can add multiple graphical objects to one window. So for example, we're going to go to the Add to Graph menu. Here we see a bunch of different options of things we can elect to add to the graph. So I'm just going to add, for example, a plane. Let's add the plane x plus 1. Okay, so here I can see the plane and the original surface both graphed in the same window. And as I can see, the intersection between these surfaces looks a bit choppy. Okay, so we can remedy this quite easily with this button here called 3D mode. You can click it a number of times, and usually this BSP mode will get you a great picture. And now we can more easily see the intersection between these two surfaces. We can control different things on the surface properties. So if I click this gear, for example, we could choose the color of the surface to be any constant color of our choosing, right? And we can also toggle its transparency. So maybe I want to still be able to see through it to see the other side of the figure. So there are many other objects we can add to the graph. Let's go ahead and get rid of this surface. We'll click the X to delete it from our graph. As a quick note, you can also use this check mark to add and remove things from the graph. Maybe if you want to keep that for later, the check mark might be more handy than Xing it out. So I'm done with that surface for now, so I'm just going to delete it. So let's choose another object to add to our graph. How about a space curve? So as always, there's an example provided. So if I add this to the graph, I can see this helix. And within this, you can control the range of t value for the input of the curve and the number of steps, which would control the smoothness of the curve. You can add in some orientation arrows if you wish. So maybe add in 4 arrows to indicate the direction of movement along the curve as t increases. Within this space curve graph, there are a bunch of really great features we can add to this slider. So clicking on the gear, I can see various things that I can add to the slider: trace point, trace vector, velocity vector, acceleration, etc. So for now, I'm going to restrict us to the trace point and the trace vector. Now when I slide the t value, a vector emanating from the origin traces out the curve as we range the values of t. I was super excited when I found this feature in CalcPlot3D because I don't know about you, but if you've ever tried to draw this out on a whiteboard, it's really challenging. So I think this is a really nice way to illustrate to students really what's going on as we range the input t and how this graph of this helix is created by the trace vector. If you have a planar curve in 2 dimensions, you could set the z component to be 0 and restrict the view of the curve to the xy plane. Again, this is the trace vector. You can see it trace out the curve as we vary t. Additionally, we could add a velocity vector, right? We know that this is the tangent vector to the curve, and we can see that it's tangent to the curve at any point. I'd like to point out a library of examples that are available to you. So if you click up here in the menu, you can scroll down to examples to see preloaded examples of various space curves, implicit surfaces, vector fields, and parametric surfaces. So for example, I'm going to add this torus twist unknot. So if I click on it, it added to the graph. So here's are the mathematical equations that correspond to this particular curve. And let's go ahead and explore some other features here in the gear. So for example, we can show the T and B frame. So if we want to show the Frenet frame here, we can add it simply with the click of a button, show the whole T and B frame. And activating the slider, we now have a T and B frame that can traverse this curve. Students usually find this particular example to be really cool. So in my mind, that's the beauty of CalcPlot3D, is being able to accomplish these types of visuals with really just a few clicks. And certainly I can customize this graph however I wish. Maybe the box is interfering a bit with my visual, and I certainly don't really need the label ticks here. So I can now maybe see this a bit better. And as you can see, there are a few things in CalcPlot3D that are computed for us. So actually at any of these input points, the unit tangent, normal, and binormal vectors are actually provided to us at that given point. Let's go ahead and see what else we can add to the graph. Okay, so we've seen functions, space curves. Let's add a vector field. Okay, so as always, an example appears, and of course you can replace these equations with whatever vector field you're interested in, but I'll go ahead and just use the example provided. So I'm going to add this to the graph. And the z component is 0, so this is actually a 2-dimensional vector field. So I'm going to restrict the view to 2D. All right, so here's a view of this 2D vector field. And as I can see, we have a little bit of overlap of these arrows. So I can control that by scaling what each of the vectors is scaled by. So maybe I'll increase it to 6. So we can see a little less overlap, and I believe that's a bit nicer picture. You can also control the number of vectors, so maybe I don't want it to be quite so busy. Maybe I want a 7 by 7 grid, and you can choose a variation of arrays, rectangular, spherical, or cylindrical, depending upon the properties of the vector field. Okay, so here we have a pretty great view of this vector field. Something I'll draw your attention to is that you can change this to a system of differential equations notation. So when I click this button, you can see that it's changed to derivatives in x, y, and z. Okay, so here we have like a direction field, and you can add in a flow line solution curve onto this field by clicking anywhere as your initial condition. Right, so here we can view various flow lines, solutions to the differential equations at various inputs. If you didn't want to view this as a system of differential equations and you were just thinking about a vector field, like in multivariable calculus, maybe you are interested in exploring the curl at a given point. So now once you click a point, you have a little pinwheel that indicates the flow of the vector field at that given point. In other words, what type of rotation would be caused by the field at that point. You can actually click this button down here to add several pinwheels at the same time. So we can see different directions in which the rotation occurs, so different directions the curl vector is pointing, and different magnitudes indicated by the speed at which these rotate. Let's see what else is available to add to the graph. We can add a point in 2 or 3 dimensions. We can add a vector, both in 2 or 3 dimensions. We can even add a text label at any position on the graph we wish. Maybe you have an implicit surface. We know that not every surface can be defined as z as a function of x and y. Perhaps you have a surface that you can't solve for z, as in the following. Right? So we can plot implicit surfaces. We can also plot parametric surfaces as well. There are a lot of things to explore within these and a lot of features within each of these types of objects. The last one I want to show you today is this region. This can create some really great visuals in multivariable calculus when you're teaching multiple integrals. So perhaps you're trying to find the volume of a solid with a multiple integral. So for example, we can define this region, this three-dimensional solid, by defining first off the shadow of the solid on the xy plane. So here we have the shadow of the solid defined by this parabola and the x-axis, so the top and bottom of this two-dimensional region, through a range of x values -1 to 1. Okay, so once the shadow has been defined, you need to define a top and bottom surface for the solid. So this particular surface, I think I'm going to change it. I think I want an upside down paraboloid shifted up 2 units. Okay, so maybe actually this is the region I'm trying to find the volume of. And for now, I'll just leave the bottom as the xy plane. So one really awesome feature that I'd like to just quickly demonstrate here are these Riemann prisms. So I'm going to show the Riemann prisms, and a bunch of options appear, number of prisms in each direction. So for now, I've partitioned the prisms in a 4 by 4 grid, and I can increase this if I want to get a more accurate approximation of the volume. So here, for example, maybe I'll increase it to a 6 by 6. Okay, so we can see the number of prisms has increased, and a really great opportunity can arise to also discuss the sample point at which the height of this prism is taken. So right now it's being taken at the midpoint of the prism, but perhaps you want it to be at the upper left or the lower right, for example. So we can have a discussion about whether this is an overestimate or underestimate and which of these sample points might provide the best estimate. And as you can see down here, the volume of the region is computed from these Riemann prisms. It's actually calculated and given to us. So a nice way to demonstrate this to students, perhaps I'll hide the top surface here, by clicking this selection. And let's go ahead and use the sliders to increase the number of prisms in the X and Y direction. So as I increase the number of prisms, we can see that this estimate of the volume becomes even more and more refined and quite accurate. So this is a really great way to, once again, with a few clicks, provide some really nice visual examples for our students. So at this point, I've created a nice example that I might wish to share during my class. What I can do is actually save all of these settings that I've created for easy reference later. And maybe I'll even improve it a bit. So I'm going to go ahead and remove the box and the axes lines. And I don't think I really care about this area down here below the z-axis. So maybe I'll also cut that off and z equals -1 or something. All right, so now I feel like I have a pretty great image that I'd like to share with my class. Maybe I won't give it away to them. Maybe I'd actually go ahead and like to start back at our fairly inaccurate estimate with a 4x4 grid. And okay, so I'm pretty happy with this view. I'd like to be able to pull this up during class quite quickly without having to set all these up and waste my students' time. So what I can do is go up to the menu and click File, Encode View in URL. So now all of the settings that I've set up here are going to be saved into this rather long URL. So if you look up here, you can see, wow, this has become quite long. In fact, I'll show you how long it really is. Okay, so there's the full URL. But everything I set up is contained within this. So once I click this, it brings me right to the settings that I have saved. So this is a really great handy tool for teachers. We spend a lot of time creating these nice visuals, so we may as well have them saved somewhere. And also this gives us a way to easily share them with our students. Speaking of being able to save our work and create easily accessible examples for our students, there is a feature called scripts. So maybe you want to save not only one image, but a series of images that you'd like to show in succession to one another. So to do so, you would create a script. I could create this script, and I'm going to go ahead and jump forward to the final example of a script. So I'm going to load a previous script that I have created in the past. And so this is a script that I created for a discussion about the line of intersection between two planes. So here I've created a series of 8 figures that I want to show in succession with one another, with some text for each of the figures. So this is actually kind of a self-guided activity that you could give the students outside of class, or you can step through during class quite quickly to show a nice visual demonstration. Here, for example, we have 2 planes. We want to find the line of intersection between them. So through a series of images, we can talk about the normal vectors to each of these planes and show the normal vectors and how, in fact, their cross product gives us a vector parallel to our line of intersection. So this is a really nice way to incorporate a series of images all together into a sequential script. So more on this later. I hope this has been a helpful demonstration of just a few of the features of CalcPlot3D. There are a lot of features that we didn't get to, but I hope that this has been a good introduction to the basics of CalcPlot3D. I wish you all the best in exploring this program and learning how to use it to enhance your courses in the future.